Good afternoon, everyone. I'll try that again without being muted. I hope you guys are having a good start to your Wednesday. I hope your Wednesday has gone well so far. We are going to continue our conversation about the function of proteins. If you remember last time, we ended where we were talking about enzymes. And today, what we're going to do is we're going to continue that, but then we're going to dig deep into an important under, an important thing to understand with respect to enzymes. So I'm going to share my screen. I'm starting with the slide deck that we ended with the last time, that one titled Protein Function Part 2. The other slide deck that I've got posted on our Canvas site for today is titled Enzymes, and I'll go to that one after a little while. So one of the things that we were kind of wrapping up with was this idea of studying an enzyme, and it's doing steady state studies. Um, and with this graph, and there's a couple of different graphs that you're going to be looking at over the next few, you know, well, for immediately the next few minutes, probably the next hour and a half or so, hour and 20 minutes. Um, but it's always important to understand what the graph is that you're looking for by looking at the y and x axes. There are a handful of graphs that will look very similar, and you'll think, oh, well, I see the curve of that. I know exactly what this is. But don't fall into that trap. What this graph is showing, it's showing the relative um, amounts of our free protein or free substrate or sorry, our free product, our free substrate, our free enzyme, and our enzyme substrate complex. So that's what we're concerned with and interested in is with respect to enzymes. Now, this is a nice, simple explanation of, or a model basically, of an enzyme and a substrate. Now, this is a good way of visualizing how do you study an enzyme? Well, and why do you study an enzyme? So, the why do you study enzymes? The first answer to that question is basically to see what they do, see what one does. And then a continuation of that, you want to know some of the kind of, I'll say, performance parameters. Performance parameters of enzymes. Now, the first two performance parameters are really important ones. The first one is your Vmax, which is also known as your maximum velocity. The other one is Km. This is known as the Michaelis-Menten constant. Now, what I chose to do this semester was I chose to introduce function of proteins using hemoglobin and myoglobin as examples right before introducing enzymes. And the reason for that is because these two kind of performance parameters, we call them kinetic parameters, um, these two kinetic parameters are very important for enzymes, but they're also very similar to O2 binding proteins. Now, if you would please go with me on a journey for a second, imagine an enzyme. I always like to think about an enzyme similar to a car. Um, an enzyme or a car, one thing that they have in terms of their performance is they have a maximum speed. They have a maximum velocity. They can only go so fast. Um, and in the event that you're thinking, oh, but what about this aftermarket modification? Okay, that's fine. That's a different thing. But just go with me on this that a car has a top speed, and that's all there is to it. So an enzyme has a top speed. That's all there is to it. You can't like give it more substrate to make it go faster. You can't, I mean, there are some things that you can do to optimize it, but it has a maximum velocity. Now, This is similar to an oxygen binding protein because oxygen binding proteins have a maximum saturation. What percent, and so a maximum saturation is where, well, basically it's 100% saturated with its ligand. Okay. So I want you to think about these two things, Vmax and the 100% saturation as being analogous to one another. Um, an oxygen binding protein, well, you change the conditions, and we can look back at this graph right here. And um, we have on our y-axis 1.0. That's our theoretical 100% saturation. Um, you can't get a protein to bind 110% of its ligand. It has a limited number of binding sites. It can't bind more than it has. So that's kind of the point there. Now, this difference between here and here, well, that has to do with kind of the practical approach that, well, this protein is going to bind and release things. Now, an enzyme kind of has that same sort of performance in that, well, it can only go so fast. So I want you to think about those two things as similar to one another. Now, an oxygen binding protein has a kind of property or value very similar to a Km, and that's none other than its P50. Now, the P50 is and I'm gonna say the PO2 or the partial pressure of oxygen, where your, I'm going to say hemoglobin is 50% saturated. Okay. So if we think about, I'm going to take these two ideas and kind of revise them. Um, and for P50, the question is, not the question, but to rephrase that, you'd say that, um, actually, I'll go with the max saturation. Your first question regarding the oxygen binding protein is how much O2 can it bind? What's the maximum amount that it can bind? 100%. Could you give me a one in the chat if you understand that as a kind of high watermark, I guess? Okay. Now, when we talk about P50, we're asking about the binding, but rather than saying how much can it bind, instead we're saying, well, how much O2 is required, and for 50% saturation. Okay. So these two questions are, I always like to characterize these questions or simplify these questions as one question is how much can it bind? And then the other question is how much does this protein need to bind that much? Could you give me a three if you follow what I said there and that makes sense, or a seven if that doesn't make sense to me? Okay. Now, when it comes to enzymes, these two things are very similar to one another. Vmax is that, well, how fast can it go? Performance question. But Km is the same thing as P50, but dealing with substrate. Km is how much substrate gets the enzyme to go half as fast as possible. And it's as fast as possible is its Vmax. Could everyone give me a Q in the chat if this makes sense, this statement right here, and a P in the chat if I don't understand that? Okay, cool. So I want to highlight one thing and then show you how you're going to see it, just so you can kind of anticipate it. Um, say half as fast as possible or half Vmax. You're going to see that simplified as Vmax divided by 2 or Vmax over 2. Okay. So understanding Km and Vmax are the two basic and the two first kinetic parameters for understanding. Oh, sorry about that. Understanding how an enzyme functions and understanding how enzymes are evaluated. When it comes to oxygen binding proteins, we look at, well, what's the P50 to compare different hemoglobin variants or myoglobin proteins. Now, if we go down to this graph right here, what I want you guys to recognize about this graph is that it looks pretty similar to this graph right here. The differences are not that dramatic, but they are there. The y-axis, for example, is your reaction rate. We can label that as velocity. Sometimes you'll see it listed as initial velocity or V sub zero. Your x-axis is your substrate concentration, which many times you'll see that simply denoted as S bracketed with the molar concentration. Now, what this graph is showing, I really like this one because if you look at each one of these dots, that's a data point. Now, I've tried to explain this in the past, and I haven't done the best job, or I haven't done, there's room for improvement in how I've explained it. Typically, when people see one of these graphs, they see the y and x axis, and then they see a line that looks like this. And that, if you look at it right here, that's a trend line. That's kind of like you went into Excel, plotted all these points, and you selected a line of best fit, and then you selected a hyperbolic line. Now, I bring that up because lots of times what people kind of struggle with is, and I know that I was guilty of this, for some reason, I looked at this graph and I said, aha, that's where my enzyme starts. And then it just gets faster and faster and faster and faster, neglecting the point that each one of these dots corresponds to a data point. So anytime you see a graph that looks like what I'm showing you right here, remember that graph, what you're seeing is the line of best fit. Okay. So what that means is that in order to construct one of these, what do you have to do? Well, here's a trial T1. Here's a trial T2, T3, T4, and so on. And so I wanted to go ahead and show you guys what T1 looks like. Whenever I say T1, I mean the very first trial. Or, you know what, I'm going to go ahead and jump to T2. T2, imagine that's taking place for some, would you mind showing the previous enzyme slide, like the for one moment so I can take a picture? Are you referencing this one? Okay, I'll interpret that as you're good to go. All right, so thank you very much. Got that. All right, so let's imagine that we have an enzyme that will take a circle and convert it to a square. Okay, I know that this is not a circle molecule and not a square molecule, but let's just imagine we have an input substrate and an output product. Or, you know what? Our enzyme converts A to B, single substrate, single product. For trial number 2, that would be this data point right here. What somebody's going to do is they are going to collect the substrate, sorry, they're going to get a test tube. Here's our test tube. And they're going to get a substrate. And they're going to get a substrate, I don't know, they're making a final substrate concentration of, let's just go ahead and call that 75 nanomolar. I'm going to put the substrate concentration in nanomolar. Okay. They're also going to get some enzyme. They're going to mix those two things in there. And so I'm going to say that this red is my substrate, and then my enzyme is blue. And there we go. And sure, they're going to have other things like a buffer. They're going to have that in there. Then just some water to bring it up to a total volume. And what they're going to do is they're going to let it incubate, let's say for 15 seconds. And after 15 seconds, what they will do is they will monitor the production of the product. Okay. So they're going to watch the product formation and the rate that that product is formed. So that would be product concentration divided by 15 seconds. Could everyone give me a 1 if they're with me and a 6+ if they're not? Okay. So you'll watch for 15 seconds and you'll see that product produced, and they'll come up with a reaction rate. And let's just say that they come up with a reaction rate that's approximately 0.035. We're going to label that on our y-axis here. Okay. Or we're going to, plot that point. Then trial number 3, I'm sorry, they're going to increase the substrate concentration. And so they'll get another test tube. Substrate concentration grows from 75 to, let's say that it goes up to 125 nanomolar. The enzyme will also be in there, as will the buffer, the water, and they're going to do the same thing. They will be, over the course of these different trials, they will be varying by increasing the substrate concentration, but the enzyme remains the same. And I'm going to go ahead and put bracket that E so that you recognize that the concentration will remain the same. And they're going to do all of these trials. And then eventually they're going to plot the data and they're going to see, oh, you know what? Whenever I went from 75 nanomolar to 125 nanomolar of my substrate, what happened to my rate? Oh, it went up. Whenever I continued increasing, and I'm just going to be drawing along this black line, when you continued to increase the substrate concentration, the velocity went up. You continue to increase, goes up. At some point, let's just go ahead and I'm going to compare I want you to look at point A and B, and then I want you to compare points C and D. With point A and point B, the rate goes up at a faster rate than between C and D. Between C and D, the amount of substrate that we had to add was greater than the substrate that we had to add between A and B. So we're getting to a point for all of these successive trials where, and I used this term earlier today, if anyone's ever taken an economics class, it has been a minute, but the concept of diminished marginal returns. This isn't an economics class, but nevertheless. the amount or as we add more and more substrate, the reaction rate will continue to increase, but will increase at a slower pace. Now, I want you to put 1 plus 2, not the answer to that, but 1 plus 2 in the chat if you understand both the statement that's in the big circle and you can visualize that on the graph, or you understand that graphically also. Awesome. Now, that's how this is constructed. You do a series of trials, you increase the substrate concentration, but maintain everything else as the same. You do like replicates of this for statistical significance, and then you'd have nice little error bars and stuff, but we're not worried about that for this. Now, throughout these trials, eventually, with a Michaelis-Menten curve, you'd be able to make an approximation of the maximum velocity of your enzyme. And as soon as you can make that maximum velocity um, prediction or estimation, then you'd be able to recognize, well, where's half of my maximum velocity? Well, that's halfway down the y-axis. There's my half Vmax. So is what you wrote in the blue circle the reason the dots get further apart on the x-axis? Yep. That's exactly it. Because, and I think that it's a little bit easier to visualize between A and B. I have an estimated substrate concentration of a difference there of approximately 50 nanomolar. So on my x-axis, that difference is a pretty narrow range. So from right here to about here. Okay, so right there, it's about 50 nanomolar. But what happens to our y? Well, that goes from about 0.035 to almost 0.07. And almost our rate doubles. And that's what it took. It didn't take a huge amount. Whereas from here to here, what's our substrate concentration difference from this point to this point? Our substrate concentration difference, it does require a little bit of an estimation. I'm going to call that about 600 nanomolar. Might disagree with my number there, but I'm just kind of making an estimation. 600, and I'm going to call this about 1200 nanomolar. Well, the amount of substrate that we added was pretty dramatic. But what did we get in terms of the return? Well, not nearly as dramatic as what we see between A and B. So, yes, to your point. Okay. Now, whenever you do all of this, you can make that estimation of your Vmax. Great. That's important. As soon as you do that, you have one performance metric where you can say, aha, my enzyme can, its maximum velocity, its Vmax is approximately, we're going to call that 0.35. And, the rate would be something like nanomolar per second or something like that. You're measuring the product per 15 seconds. So then you when you divide it by 15, then it's going to be nanomolar per second or units of your product per second. Okay. Now, if we go back to this slide right here, the statement was, well, what's our Vmax? That's how fast can it go? What's our Km? Km is how much substrate gets us there. And in this case, okay, y-axis is all about velocity, all about rate. X-axis is about amount. So in this case, we would make the coordinates, see the coordinates, and we'd say, okay, well, here is half of V max, dot, 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 dot. Okay, well, that looks like that's about 350 nanomolar. Yeah. So it took a km for this would be 350 nanomolar. Okay. Now, what's the significance of 350 at this point in time? There isn't really any. I'm just saying that number because that's what it looks like approximately to me on this graph. Now, this is what I'm trying to illustrate here is the similarity or the parallels between P50 and Km and your 100% saturation and your maximum velocity. Excuse me, I apologize. Okay, now this is a Michaelis-Menten curve. We will look at another curve in just one moment, but what I'm going to do right now is I'm going to switch my share. Now, I want to show you a table that basically to me works as like a sales pitch for why are enzymes interesting. So if you look at a reaction, you have an uncatalyzed rate. So how quickly can a reactant, shown here, this reactant be converted into this product? And in this case, this reaction that's shown below, well, our reactant right here is losing a CO2. So this is a decarboxylation reaction. Okay. So this molecule gets decarboxylated. And you know what? It happens at a rate of approximately 28 times 10 to the negative 16 inverse seconds. So it's a very, very small number. So if you have an amount of that, for half of it to be gone would take approximately 78 million years. This enzyme that catalyzes this reaction or that can catalyze this specific reaction is OMP decarboxylase. Now, keep in mind, this is our uncatalyzed rate. This is the enzyme that does the same thing to catalyze this reaction. OMP decarboxylase, when that's present, well, it's going to go at a different rate. It's going to happen at approximately 39 per second. And this is ultimately a rate enhancement, which is a ratio of the rate constant of the catalyzed reaction over the uncatalyzed reaction to be 1.4 times 10 to the 17th. So long story short, this is much faster. So enzymes are capable of accelerating reactions by, well, 1.4, 3, 4, 5, 6, 7, 8, 9, 17 times, 17 zeros. Faster is the point. Okay. Now, what we're going to get into here is we're going to talk about enzyme inhibition. I'm going to talk about a couple of kinetic parameters, but we've learned a little bit about how a reaction can be interrupted, or sorry, how a reaction can naturally take place, but then we're going to learn now about how an enzyme can be interrupted. So Km, we've learned it as this is the substrate concentration that gets our reaction to Vmax over 2. That's one way that I want you to think about it. Now, if you remember this notation here, E plus S, it's an S, not a 5, yields ES yields E plus P. You'll remember the reverse reaction going from the enzyme substrate complex to the enzyme plus the substrate is also possible. The enzyme plus the product going back to the enzyme substrate reaction is possible, but we have a tendency to leave out that reverse reaction just because of how unlikely it is to occur. Now, Km, to put another way, is it can be viewed as it's our forward, it's a ratio of rate constants. K sub one is the rate constant about the formation of the ES complex. K sub minus one is that ES complex breaking down. K sub two is ES going to E plus P. So our Km is effectively a combination of, well, what are the combined rates of those rate constants that lead to the breakdown of ES, either from ES to E plus S or ES to E plus P, divided by, well, the rate constant for the formation of ES. Now, what I think is I think that it's very helpful to think about Km in this sense right here. We're looking at it as, well, it's half of our maximum velocity, or it's the substrate that gets us to half of the maximum velocity. If you think about all of these steps right here for these different rate constants, we have the formation of our enzyme substrate complex, but we also have the kind of the breakdown of our enzyme substrate complex. So that's what we're kind of balancing there with this expression right here. Now, when our K sub 2, this one right here, is considerably less than our K sub 1, Km is going to be reduced to K sub 1 over K over 1, which is effectively our KD. Now, this can be equated to a dissociation constant. Now, the takeaway from this, aside from this right here, is that a small Km is our good indication that we have very tight binding between our enzyme and substrate. Now, I want you to think about that as, so a small Km means our enzyme tightly binds the substrate. And I want to give you a graph, or a graph with a pair of kind of modeled enzymes. So the first thing that I'm going to do is give us a y and an x-axis. Now I'm going to draw a hyperbolic curve for one enzyme, and that's going to be represented by this red line. And then I'm going to do another one with this gold line. The idea whenever you look at these two lines, I'll call them R and G, red and gold, is that they both eventually meet or reach the same maximum velocity. So their overall rate, if you provide them with enough substrate, basically, from here on, if you give them enough substrate, they're going to be catalyzing the reaction at the exact same rate. Now, with that in mind, if the maximum velocity between these two enzymes is effectively the same, what makes them different from one another? I mean, the answer is the Km, but between these two, R for red or G for gold, which one of these two enzymes has the smaller Km? And to answer that, if you're comfortable and ready, you throw it in the chat. But if you're not, let's look at our y-axis. Our y-axis, this right here, is our Vmax. So then we cut that number in half. And I'm not putting any specific numbers down because that's not super important. This is our Vmax divided by 2. Dashed line. I'm going to go dashed line all the way out here. And that down here. My x-axis is labeled as our substrate concentration. Which number do you think is going to be smaller? The number where A is or the number where B is on that x-axis? A, totally. So what this means is that between R and G, A and B, these points on this x-axis represent two different KMs. Well, gold will correspond to the enzyme with the lower Km. Could everyone give me a 9 in the chat if they see that and they understand that? Okay. So between these two enzymes, Km is the thing that differentiates these two that differentiates the two enzymes. Red with a larger Km indicates that it does not bind the substrate quite so tightly. Now, we're going to look at Km in a couple of different ways. So the first thing that I want you to think about is the smaller the Km means it tightly binds a substrate. At some point, though, you got to imagine, well, we don't want it to bind too tightly because then, I mean, does it hold on to it indefinitely? Does it ever release that substrate? We need that substrate or that product to be released. So, as sort of a case study of this, I want y'all to look at this. I think that it's good to compare substrates, multiple substrates for the same enzyme. Okay, there's an enzyme known as hexokinase. When you see hexo, I want you to think 6. So hexokinase is an enzyme that acts on 6 carbon sugars. There's a number of different 6 carbon sugars. Glucose is a 6 carbon sugar. Fructose is a 6 carbon sugar. Okay. So hexokinase, in order to catalyze its reaction, is going to bind to ATP and a 6 carbon sugar. Now, between these two sugars, glucose and fructose, and I'll go with G and F. Tell me which one of these two sugars will hexokinase bind to more tightly? Is it G for glucose or F for fructose? Add it to the chat. G, because these values right here are KMs. So what we need to do is compare that 0.05 and 1.5 millimolar. So hexokinase, I'll take this and kind of synthesize a sentence. Hexokinase has a greater affinity for glucose than fructose. Now, it's good to be able to look at those numbers and kind of synthesize that idea, but I want to kind of elaborate on that with this example. If both sugars were at 5 millimolar, but for this, what I'm going to do is I want you to think about it this way. You've got hexokinase, and you feed hexokinase, let's just say you give it 1 molar ATP, an excess, a huge amount of ATP. And then you give it 0.05 millimolar glucose. Okay, so let's think about what this means. What does the Km mean? So Km is a measure of affinity, sure, but more than that, it's our way of thinking about, well, how fast is our reaction being catalyzed? If you give hexokinase, which I'm going to label as HK, glucose, a concentration of 0.05 millimolar, then what I want you to tell me is, will first Y or N, will hexokinase be catalyzing this reaction? So you're giving hexokinase 1 molar ATP and 0.05 millimolar glucose. It needs ATP and glucose to catalyze the reaction. Will it catalyze the reaction, Y or N? Not asking about rate or anything yet, but will it catalyze the reaction? Yeah, totally. It needs those two things, and you give it those two things. Okay. Now, since we're all, or since we've pointed out that it will catalyze the reaction, I'm going to ask the question, how quickly will it catalyze the reaction? And I'm not looking for a quantifiable unit or a quantifiable value, but I'm going to give you three options: A, B, and C. A is it's going to catalyze the reaction at its Vmax. B is this will catalyze the reaction above Vmax. And answer option C is it will catalyze the reaction below Vmax. Give me a response in the chat. If you give this enzyme 1 molar ATP and 0.05 millimolar glucose. Seeing lots of A's. Let's think about this graphically. Oh, that's not what I wanted. Let's think about a graph here. Here's my graph. Maybe B. Okay, it looks like we're trending towards B. I'll draw my Vmax. And then there's my line representing, that's my line of best fit. So the only two things hexokinase needs to react are ATP and a 6-carbon sugar, for all intents and purposes, yeah. So we're giving it everything it needs. The reaction will take place. But my question now is, how quickly will the reaction take place? Now, my y-axis is rate or velocity. And, let's go back through the answer options. We got at Vmax, B is above Vmax, and C is below Vmax. Remember how I talked about a car has a top speed, just like an enzyme has a top speed. What are the chances that an enzyme will go faster than its maximum velocity? Sammy, I see some, okay. It's not going to go faster than its Vmax, so B is out. Would it be C due to the Km being only half of the Vmax? Spot on. Great job, Sammy. That's awesome. So what we want to do with this is we want to look back. Okay, so we have our Km for glucose, 0.05 millimolar. How much glucose did we give hexokinase? 0.05 millimolar. So effectively, we gave our enzyme glucose at exactly, it's Km. So at best, it's going to be half of its Vmax. So if you were looking at this graphically, that right there is 0.05 millimolar glucose. Now that's a tough one to wrap your mind around. So what if I were to say, or actually, um, instead of giving it 0.05, we gave this enzyme, let's go with 0.5 millimolar. Is our enzyme going to be going faster at 0.5 millimolar of the substrate than 0.05 millimolar of the substrate? And to that answer that question, basically is 0.5 greater than 0.05? Yeah, because there's more. We've given it more substrate. You could think about the substrate as its fuel. You've given it more of the fuel that it needs. Okay, so I'm going to add a slide in here so that I can elaborate on this. And I'm gonna try to construct a table. So we'll go to our enzyme, HK, hexokinase. And I'm going to make this table for our substrates, Km. Hexokinase has three substrates, ATP, glucose, and fructose. That would be, what was our substrate for this? 0.4 millimolar, 0.05 millimolar, and 1.5 millimolar. Okay. So when you're setting up a hexokinase reaction, you need ATP and I'm going to say glucose or fructose. Okay, those are our options. Now, if we give, and we want to be kind of thoughtful of and aware of these amounts. So let's say that we got a beaker. And in this beaker, we've got a solution, we've got our enzyme. This is our enzyme floating around. Hexokinase floating around, HK. Doesn't matter how many of those I draw. I'm just gonna, yeah, there we go. Hexokinase is in. And in this beaker, we add 5.0 millimolar ATP. Y or N, does this enzyme have enough ATP to catalyze its reaction? Not asking about speed, but does it have enough ATP to run the reaction? Does. Now, if we were to look at this graphically, this is our Km, so this is approximately 0.4 millimolar. Are we here or are we here? Y? X or Y, roughly? We're at the Y because we have given it more than enough of this substrate. Okay. So now I'm going to erase this first graph. We've given this reaction lots of one of our substrates. Okay, so we're good. Now, I'm going to give you guys two options. We're going to give our enzyme 0.005 millimolar glucose. And then I'm also going to put in here 1 millimolar fructose. Actually, no, you know what? I'm going to go with 1.5 millimolar fructose. So 1.5 millimolar fructose and 0.005 millimolar glucose. Given the choices or given the options, fructose versus glucose. Well, let's talk about fructose first. Will our enzyme be able to act on and react with the ATP and the fructose? Why or one for yes, zero for no. If you've already answered yes, don't worry about it. Yeah, it's going to be able to act on the fructose. There is enough fructose, there's enough ATP. Glucose. That's well, we're looking at about 1/10 of the km. I mean, will it react? Yeah. There's not a lot there though. Now, if this enzyme, this is going to personify it a little bit, but if our enzyme is like, I want to go fast, if it's Lightning McQueen from Cars 1, 2, or 3, it says, I want to go fast. Which substrate is it going to pick? Which substrate is it going to have a preference for? G for glucose or F for fructose, considering their KMs and the amounts that are present? Perfect. Spot on. That's absolutely right. Because if it binds to that fructose, it's going to be able to go at half of its maximum velocity. If it binds to glucose, it's going to be going slower than half of its maximum velocity. Now, the KMs are relative measures of affinity. Sure, it has a greater affinity for glucose, but this number right here, that's telling us what is in there. That's telling us the concentration of glucose in that solution. We know that it has a Km of 0.05, but there's not a lot in there. So it's almost like, yeah, it really wants it, but there's nothing for it to work with. So when it comes to questions of, like at the bottom of this slide, I'm going to duplicate this slide and then clear out all of my drawings. Oh, go. And you know what I'm going to try to remember to do is I'm going to try to remember to save this slide deck with all my markups and load that on our Canvas page so you have that. When we go down here, it's useful to compare Km for a common substrate used by several enzymes. Okay, hexokinase and glucokinase. These two enzymes will both bind to glucose. Is it H or G that has a higher affinity for glucose? These are the Km values. Which one of these has a higher affinity? Well, the one that has the higher affinity is the one that has the lower Km value. So absolutely, Esperanza, H. And Emma, you're right on. So hexokinase has a higher affinity for glucose than glucose. Or that, sorry, hexokinase has a greater affinity for glucose than glucokinase has for glucose. So one way that I always kind of think about this is you have two enzymes, and if you had a mixture, let's say we had a solution with hexokinase and glucokinase, and then you added a glucose molecule, and you said, hey, fight it out, guys. Well, hexokinase is going to be like, I want that glucose more. And glucokinase is going to say, okay, I guess I want it too. Oh, you got it. Oh, well. Okay. So then this next point, which of these enzymes, hexokinase or glucokinase, when you consider there are two KMs for glucose. Which one is operating at maximum velocity when glucose is provided to both of them at 4 millimolar? What I think is really good for this is to draw a graph. And it doesn't have to be a very involved graph. You're drawing the same thing, but you're just labeling them differently. This is for hexokinase. My Km right here is 0.05. Okay. Then for this one, 20 millimolar. Now I'm going to draw a red line to indicate where I am on my x-axis whenever I've given my enzyme 4 millimolar of the substrate. Well, I'm about here. Where does that match up? Okay, well, that's not at my Vmax, but I'm pretty close to it. Then on my other graph for glucokinase, 4 would be right about here. And so I'm right here, boom. Okay, that is, oh yeah, that is considerably less than half of Vmax. Because if this is Vmax divided by 2, I'm right here, so I'm lower than that. Could you give me a 9 in the chat if that makes sense? Okay, wonderful. All right, so Km is a measure of affinity. It's also a way of looking at how much does one enzyme want to substrate over another enzyme. Now, what we have in terms of kinetic parameters are Vmax and Km. We've looked at Km in a couple of different ways. We've looked at, well, how do we actually kind of track that information? And now we're going to talk about turnover number, also known as Kcat. This is a measure of catalytic activity. And what we do for calculating Kcat is we are looking at the number of substrate molecules converted to product per enzyme active site per unit of time. Okay. So Kcat is our maximum velocity divided by our enzyme or um, our enzyme active sites per time. Okay. Now, what this is doing is effectively helping us look at enzymes that have multiple active sites. So Kcat, when we're looking at something as kind of thinking about it as what's better, what's good, the larger the Kcat value, kind of the better. Now, this number is beneficial because when we use this versus our Km, our Km is a measure of, well, binding affinity. And Kcat is, well, how much substrate gets converted to product per active site unit time. Km versus Kcat is a measure of effectively our catalytic efficiency. And this is kind of balancing those two variables and saying, well, how quickly or how much are we converting? How much substrate are we converting to product? And how quickly or how tightly do we bind that substrate? If you have a Km that is extremely low, then you're binding it very tightly. And so the amount of substrate that you're converting to product is going to be impacted by that. Now, you want to kind of balance those two things, like what we see here with acetylcholinesterase. This shows a Kcat of 1.4 times 10 to the fourth and a Km of 9 times 10 to the negative fifth. So this is a very low Km, not an extremely large Kcat, but the combination of those two gives us a very highly efficient enzyme. So the higher this ratio, the more efficient an enzyme is, the more substrate that it can bind and convert to product and subsequently release that product. Okay, so what we're going to do now is transition into inhibition. Now, when it comes to enzyme inhibition, sorry about that, typo. Um, I'm going to show you the patterns of inhibition, and then we're going to call it a day. So many substances bind to enzymes and decrease the velocity of the enzyme catalyzed reaction. These are known as inhibitors. They're very important for a number of reasons. They can be used to get information about an enzyme structure. What are the enzyme site, or sorry, the active site amino acids? They can be used for understanding the chemical mechanism. So where do electrons get pushed to and from? They can also give insight into regulating a metabolic pathway, and ultimately they can be very beneficial for drug design. Now, when we talk about inhibition and inhibitors, we're typically talking about reversible inhibitors. These are substances that bind to an enzyme, but they can be released. So that binding is temporarily, binds, holds on, releases. Now, irreversible inhibitors are substances that cause inhibition that cannot be reversed. So this would be an example, or an example of this would be something like a protease, something that cuts a covalent bond or a peptide bond, and it's toast. That enzyme no longer functions. Now, the inhibitors act in a number of different ways. Um, the most common types of inhibitors that we will talk about in this class are competitive, mixed or non-competitive, and uncompetitive. I want you to make sure that you recognize that uncompetitive and non-competitive are different from one another. In addition to that, I want you to be sure to recognize that the models that we're going to look at, the patterns that we're going to look at, are all kind of, they're not theoretical in the sense that enzymes may or may not work this way, or inhibitors may not work this way. Instead, this is a kind of a design of, well, this is the definition for what a competitive inhibitor does. And I say that because when an inhibitor is designed, it might be something where you're like, okay, well, I'm going to design this molecule to stabilize an ionic interaction between these two amino acids. And therefore, I expect it to behave like this. I expect the Km to go down. I expect the Vmax to go down. But what actually happens? So there are three major types of inhibitors. They are a competitive inhibitor, uncompetitive inhibitor, and a mixed or non-competitive inhibitor. This one down here is the one that we will spend not the most time on, but we'll spend a bit of time talking about this, distinguishing it from the other two. Now, for today, sort of as a takeaway, I want you guys to feel comfortable with a competitive inhibitor and an uncompetitive inhibitor. So I'm going to focus on those now. Now, a competitive inhibitor competes with a substrate for the enzyme substrate binding site. So I always draw my enzymes, not always, but often draw my enzymes as a little Pac-Man figure. Now, the active site is where that substrate's going to bind. And I'm going to go ahead and say that this is a pizza-shaped substrate. So this kind of has a natural landing place. Oh, that looks like that substrate will bind right in there in Pac-Man's mouth and done. An inhibitor would be designed, or you might design, of course, there's naturally occurring inhibitors, but you might design it to look like that because, hey, this part of the inhibitor looks like it could fit right in there. In which case, we'd have two possible outcomes. We have one in which our Pac-Man enzyme has bound the inhibitor, and then one in which so here is our enzyme binds the natural substrate, and then here is our enzyme binds the inhibitor. Okay. Could you give me an A in the chat if you follow these two possible outcomes? Okay. Now, this enzyme binding to the inhibitor is reversible. So it can bind it, hold on to it, release it. What I want you guys to do, and what I just illustrated was this starting point, these two outputs. This right here is ES, and this right here is EI. Now, like I said, this EI could disassemble. It could dissociate, in which case you now have the free enzyme. And that free enzyme can bind the substrate. What I've got here is I've kind of got a situation where I'm going to erase my ES and EI models. And I'm going to draw another few copies of the inhibitor. If we imagine that the inhibitor or the enzyme has an equal affinity for the substrate and the inhibitor, based on what I've got going on in the upper left-hand corner of the screen, what do you think is more likely to form? EI or ES? Add that to the chat. EI. This is the time of the class whenever I mention St. Louis area rapper Nelly was really popular when I was in high school. He had a song where he'd say EI, EI. Uh-oh. Still don't know what that means. Now I'm going to change the situation. Adding more of the substrate. More and more substrate. Um, Based on this updated model, and sorry, my scale of the substrates is a little bit off. What do you think is more likely to form now? EI or ES? ES. Okay. So would you agree with, and if you would, please put a 6 in the chat. Would you agree with the statement that, well, if you add more substrate, you can outcompete the inhibitor for the enzyme? At a 6, if you agree with that. A 6 if you agree with that statement. Yeah. That is kind of the principle behind competitive inhibition and a competitive inhibitor. You can outcompete the inhibitor with more substrate. Okay. So what that means effectively is, let's say, if you, what is not impacted, or okay, actually, let me rephrase that. Um, looking at, I'm going to ask this question. Do you think that this inhibitor directly impacts the conversion of ES to a free product and a free enzyme? Wire N to the chat. So in other words, if the ES complex is formed, is there any indication that the inhibitor will like stifle that or slow it down? Why? Yeah. What we've got is the inhibitor and the substrate, they'll fight it out for the enzyme. But if ES forms, then the inhibitor can't do anything to stop that. Or sorry, as soon as ES forms, the inhibitor says, well, I'm not interested in ES. The inhibitor is only interested in the free enzyme. So in other words, my question is, will the inhibitor slow this step right here? It won't. The inhibitor does nothing. I does nothing to this right here. It can certainly slow the formation of ES, but it's not going to slow down the actual product or product generation. So what that means in terms of our kinetic parameters is the competitive inhibitor doesn't change Vmax. It doesn't change, you know, it doesn't change the top speed. What a competitive inhibitor does, however, is it alters this ES or the formation of that ES. So a competitive inhibitor will alter slash slow, maybe not slow. I'm going to erase that. It will alter the substrate amount or the substrate concentration required to reach Vmax over 2. So in other words, what that means is that a competitive inhibitor causes the Km to go up. So a competitive inhibitor will cause the Vmax to be unchanged. A competitive inhibitor will cause the Km to go up. Those are your two important points about a competitive inhibitor. So I think we're going to go ahead and call it a day there. We'll tackle our other models of inhibition on Monday. I'm going to stop my share. Like I said, I'm going to save this slide deck with these markings so you guys can have that. I'll upload it a little bit later. I'm going to stop my recording. I'm going to say that